solve problems, but it's going to lead to a lot of very interesting conceptual question, where is the missing momentum, where is the missing angular momentum, where is the missing energy, right? Things like that. But let's start from the beginning. This problem number 26 is what you have is the loop here with the P field, let's say, going inward everywhere, right? With the resistance R as M, we give this plot of velocity, right? I didn't take this in class, part of the right? But let's do it again. There is nothing wrong in doing things over and over. So what will happen? This is the principle of magnetic braking, right? This is, what you have is a flux that is a function of time. So what happens is this length changes with time, right? Let's call this xt. Let's call this W. And the B field here inward, so the flux is BWX, right? And then the derivative change of the flux, and it's just BWX dot, right? And where is the direction of the induced current? The direction is the best thing to do is always to use Lenz's law, right? And now you should be very familiar with Lenz's law. It's not a law, it's just a way to remember things. So in this case here, the flux is, as this move to the right, the flux increases, right? Lenz's law says that you will induce a current, so that create an induced B field that try to counteract that increase in the flux, right? So there will be an induced current going down. In this case here, you can also use Lorentz force. Phi cross B will give you a force that way, right? That will create an induced current. Either will work, right? Lorentz force, right? This is the only part that's moving, that bar, right? On a frictionless track. Then or use Lenz's law to give the direction, but the magnitude of the EMF is just phi dot, and then it's just BWX dot, right? And this creates an induced current, and the induced current is just this. You remember from chapter 4 is the EMF divided by the resistance. And for simplicity, I lump all the resistance over here. Or the problem, lump all the resistance over here. Okay, so this becomes BWX dot over R. So this is what makes a problem always very interesting, is that there are many steps, right? Because you're not done here. That current, the induced current, will interact again with the B field to give you that reaction, right? To give you a retarding force. And so what happens is that you have I going that way, right? Interacting with the B field, I cross B, give you force that way, right? That reaction force is, what is it? Is I, B, this is the force per unit length, times the length of that rod, which is W, right? And I plug in the induced, this is the induced current, right? So what you have then is just V square W square X dot over R, right? That's the force. So the acceleration, X W dot, then is equal to, the force is in the minus direction, right? So the minus X direction, right? So X W dot becomes minus F over M, right? Is this F? So it becomes minus E squared W squared over MR X dot.
So we're asking for the acceleration of the back force.
Yes, this is the acceleration, right? It's of deceleration. Okay? It's a double L somewhere, double C somewhere. So what does this give you? The problem tells you that at the beginning, at time equal to 0, right? V is equal to V naught, right? So you can set the time, choose the time properly. At time equal to 0, V is V naught. So with that initial condition as a boundary condition, then this has a solution x dot as a function of time. This is V naught e to the minus. Let's call this thing alpha. Well, let's not use alpha because that would confuse you, right? Because we already use alpha in AC circuit for in AC circuit. Alpha is R over 2L, right? Let's use gamma. At some point, of course, you get alpha, actually. So that will decide. Where does the energy go? That's the question, right? I mean, these are all very straightforward. We've done this before, but I think the problem asks, if I'm correct, the problem asks for what happens to the energy. Well, the problem actually asks this way. What about conservation of energy? A asks for such type of stop, right? A asks for does it decrease? B asks for how far does it go? How far does it go, by the way? Right, I give it a kick. Let's call this x equal to 0. Right, that's when I give it a kick. Right. Then x as a function of time, and this is an integral of dv, right? Tx. So it's an integral from 0 to infinity. Right? This thing never, ideally or in theory, formally, it never really stopped, right? It's an exponential decay. So you have this is dt, integral from 0 to infinity, dt, right? But it will reach a finite distance. I mean, it takes forever, but there is a limit. Okay? And then you can calculate that. Where does the energy go? That's part C. Because initially, you have kinetic energy, right? It will all get dissipated in the system, right? The rate of dissipation, as you know from chapter 4, is R squared R, right? This is from chapter 4. By the way, the whole ENM is one big thing, right? Like, so for the finals, this is a digression. I'm not going to separate problem like, okay, this is a static problem, and then we completely blend it. More emphasis, of course, on the latter part of chapter 5 and chapter 9. Right? So a lot of things, say like Gauss law, will be implicit rather than explicit. Right? So Gauss law will be used to solve other problems within the static. Right? So yeah. Case in point here, this is from chapter 4, but you have to remember it. And this is the rate of energy dissipation, right? This is power. Right? So the total energy dissipated is an integral of PR. We might call it PR dt, 0 to infinity. Right? And hopefully, if everything is what we understood, the way we understand things, then this will just give you what the initial energy, right? 1/2 and V squared. That's the idea, right? So if you plug in the current, where is the current? Again, current, induced current, right? Induced current is equal to, where was it? VW over R x dot as a function of time, right? If you plug this into the expression for the P and integrate, right? So you'll have an integral of V squared in there, right? And V is of course given by V naught, given minus gamma T, right? And when you do that, you should get 1/2 mv naught squared. In this case, it's pretty straightforward. That's what you should get.
If all of the kinetic energy is dissipated into that through the resistor,
Yes,
then doesn't it have to stop?
Oh yeah, it stopped, right? I mean, it stopped at this is mathematical solution. Eventually, friction comes into play on that.
Right, but like say, even in an ideal case.
It does come to a stop at time equal to infinity.
Okay.
Right, yes, right. I mean, this goes to 0.
At infinite, yeah. Mhm.
Okay. So here, in this case, there is no ambiguity at all. You'll find that everything just conforms with your understanding of conservation of energy and momentum. How about momentum here? Initially, there is a I gave it a kick, right? So this is not part of the problem. I'm just trying to, end a class with asking questions rather than answering questions, right? The whole thing is about asking more questions, and you learn more of this. In fact, I don't think I learned all of this until myself in the end. But initially, there is a momentum. The initial is mv naught, right? And at the end of the day, there is no more momentum. But it's confined not at time equal to infinity is here. Right? What happened to conservation of momentum? That's the first question. I'm going to move on. Second problem, and any question on this? This is, by the way, actually a principle for doing magnetic braking, right? I mean, a variant of this problem that you can have on an exam is that instead of something like this, right? Say you have a loop of known dimension, right? W and H, right? Going into a region of magnetic field, constant magnetic field of length, say L, right? You give it some velocity v, right? As it enters the region, you start with a back EMF, you start with a retarding force, right? It starts to slow down, right? And then it exits, right? So it starts with a v, but when it completely exits here, this is the region where there's a force. Or slightly bigger, right? Because it encountered a force when it's reduced and it's like this big, right? And it's right? But when it exits the area, there is no more acceleration here, right? So there's v bind. You can see that maybe somebody at an exam said, well, I give it a v naught here, there is a region of magnetic field. What is the exit velocity? It's not that difficult, but it's not that straightforward either, right? Because what happened is that as it entered the region, right, V changes a function of time, right? So the interaction time you have to know, right, when this actually exits. Unless you can, because you can use conservation of energy here, right? But conservation of energy when you have a magnetic field is involved is a bit more complicated, right? So as you see, things like that happen, right? So the easiest thing is to actually do it not using conservation of energy, right? To just calculate dynamically what happened. Right? So in this case here, if I want to know what is the final velocity, right, instead of doing conservation of energy, then I have to find how long does this organ interact. Right? Okay. So what happened here? So t, the total time t is an integral of how does this work? Or the distance traveled, right? No, sorry, that's what I meant. Not just interaction time, but also distance travel. Distance travel as a function of time. And then you have to match it with this length. So that gives you a slightly more complicated integral. Because you know the velocity as a function of time. And then delta x then is just an integral of v and t, right? And we know what delta x is. Delta x is some number like that. Okay, I'm not doing it because I guess I'm limited here. So I don't have an exact number. But you see my point, this is a good example problem. The hardest part is actually to calculate the relationship between the distance traveled and time. Right? Because your expression for the velocity is v as a function of time. Right? This you can calculate easily. There is no difference. This calculation is exactly that calculation. But instead of interacting for infinite period of time, you interacted only for a finite period of time. Yes, one possible problem, but problem number 720, what is the next one? 727 is related. No, 727 is actually pretty simple. So let's do 730, because it's related. No. We have one more. Oh yeah, no, 727. Inside is B naught, is mu naught, and I, right? Okay. And say I have a sinusoidal current, I naught equals omega t. Okay. So the P field oscillate inside, and I have a loop in the middle. The problem has a loop in the middle of radius r. Right? And it acts to calculate for the induced current in the ring. Okay. So this is a radius r, has a resistance big R, same thing, calculating this current. Okay. And this should be pretty straightforward. What is the induced current here? Well, to do that, you calculate the flux, right? And the flux is just B naught. B field is constant everywhere. Times the area. Right? The area of that ring, right, is just 5 r squared. Right? So the total flux then, as a function of time, is mu naught pi n r squared I. Right? So the rate of change of the flux is just that. Right? And the EMF then is just equal to this. Right? So the induced current is EMF over R, then it becomes mu naught pi n r squared over big R. Big R is the resistance. And then times the dot. That's the induced current. Right? So So what happened here in the, there is also because of the induced current interact again with the P field, right? But in this case, that's pretty straightforward. This is what happened here. The induced current, the P field everywhere is like that, right, in the Z direction, right? So there's a force here, the unit length I cross B, right? Okay, so you have I cross B, there's a force out here. This is the Lorentz force. This is the I times B per unit length. So if you have a non-rigid ring, then it will stretch.
How did you determine the direction of I induced if I naught changes direction?
Oh, yes, then it will oscillate also.
Okay.
Yes. So here, just
Like
make sure that everything is correct, right? So when I is, maybe I should use sine, but the book asks for cosine, the book use cosine, but if this is sine, right, it doesn't matter, right? This is just a shift in time,
Right.
right? I is like that, right?
Right.
So there is an increasing flux, right? Increasing flux that way, right? So by Lenz's law, then the induced current
Keep going the other
will
way.
be going the other way,
Yeah.
right?
To create a V field down,
Okay, if you down,
which will
and
then create a force.
V cross B will, so it also,
So we'll contract.
you're right, sometimes, I guess I wasn't thinking about that, but, yeah, sometimes the force actually will force the ring to contract, right? So it will also look back and forth like that. Question on this?
I have a question for this problem.
Yes, which problem? This problem?
Yeah,
Uh,
when the ring is inside the magnetic field,
Yes.
will it experience any force?
Yes, good question,
It's like-
right? So if this region here is this strip is thin, right? Wait, if this strip is actually thick, sorry,
Yes.
right? If it's very thick, so when the loop is inside, then there is no force, right? Because there is no change in the flux, right? Also, you can use Lorentz force, right? Because the Lorentz force here, V cross B is that way, right? And then the Lorentz force on this side is also that way, right? So the integral, the line integral of Fn over Q, right? The Lorentz force per unit charge over dl is 0. Because the part of the EMF coming from this section cancels that part from that section. Right? So when you're completely inside, there is no force. Right? I mean, to analyze this simpler, then instead of like maybe this complicated of an integral here, right? Just to consider a situation where the field is everywhere here, and you just enter in. Right? And at some point, after you completely enter, as Jackie was saying, right, it's ghosting. Right? So the velocity goes like it's exponentially decaying, and then it becomes, and at some point there is a kink, and it becomes just a constant velocity. When the whole loop is inside, you have a constant velocity. Right? I can ask, well, what is this final velocity? Then make the integral slightly simpler. Okay. So, next question. I mean, I don't want to pursue that yet, right? We can look into the consideration of displacement current later on. But in that case here, because the blue field is all just uniformly upward, actually in the Z direction, right? Then all you have is a stretching of the loop, right? But what if you are at the end of a semi-infinite solenoid, right? Remember, the B field flaps out, right? In fact, you know from the homework, it actually goes straight like that, right? Okay. So if I have a loop like this, right? There is also an induced current, right? Suppose that's just for simplicity, let's consider that the I is only increasing, right? So you have an induced current going the other way, right? This is the I induced, right? So it interacted with the with not just the actual component of the B field. That's not really interesting because they only stretch the ring, and if the ring if it's very rigid, then it won't stretch. Right? But there is also right the radial component of the B field. Right? So you have I cross B. What is that? Let's look at it this way, right? I cross B, so there's a force up. This is the back reaction force, right? So there's a force that will just pop this ring out.
Is I going up or is it going in?
Which one? I is because the solenoid here has an increasing current, right? So the B field, which is as a function of time, is mu naught, and I, the B field also increases, right? So you have an increasing flux, right? That will create an EMF, an induced current that way, right? The induced current interacts with the B field, causes a force to go upward, right? So what happened? Right? This thing pops out, right? But who's doing the work? Where is the energy coming from? That's the issue, right? Who's doing the work? And to make things more complicated, all these have an answer, by the way, right? Unlike all this paradox in quantum mechanics, sometimes there's no answer. All these have an answer. But it's just an advertisement for learning it more in the future, I suppose, because we're coming to the end of a class. Suppose instead of a ring, instead of a conductor, right, I have a ring with a line charge distribution. Right? And the ring has mass m. Okay? Same problem, right? So what happened here? What happened is there is this part. From Faraday's law, remember Faraday's law? Right? The L is equal to minus D over to right? Okay. So what you have then, you have the electric field is going to be completely tangential. You have 2 pi r e tangential, right? Is equal to the rate of change of the flux, right? Is equal to the flux coming from the solenoid, right? So there is an E field, right? What is and the direction of the E field is the same length slot, right? So there's an E field going back. And the electric field interacted with the charge. Right? Okay, and these things start to rotate. There's a torque. In the ring. And the torque is given by just lambda times E, which is torque per unit length, times the length of the ring, because the electric field is just uniform all around the ring, which is 2 pi r, right? If this is the radius of the ring, right? And then the torque is of course force times the moment, right? So you have a torque equal to lambda 2 pi lambda r squared, and E you get from that formula, right? So there's a torque that is start the rotation. So what happens to conservation of angular momentum? And it's not all observed.
Since there's like a force being exerted on the ring, won't there be an opposite force exerted on the coil? So then maybe the coil will rotate the other way?
Yeah. There is also that. So what happened is the problem is more complicated. So there's an induced current, right? And there has induced B field. The induced B field create a change of flux in the solenoid. Is that what you're saying? No, that's what I was.
No, well, I wasn't quite saying that. I was just saying like by Newton's third law, maybe.
That this will rotate.
Yeah.
But this can be especially massive. So, well, yeah, you can look into that. I haven't looked into this very carefully. But no, the answer is actually not that. It's not very satisfying. But to analyze it is actually very complicated.
But like,
but no, but the answer is not that. The answer, it turns out, this is, I don't know if we can do this at the end of chapter 9, because we'll be doing E and M wave, pointing vector. So there's a momentum associated, anytime you have a field, E and B, right, there's an E and B. This is all just advertisement, this is one dimension. If I have an E, and I have a B, anytime if this thing is non-zero, I have a momentum. And there is also, because of that momentum, you can associate an angular momentum with it. So in the E cross B, there is an angular momentum. So here, right, what happened is initially by having that charge, having that lambda over here, right, there's an E field everywhere, right, because this line charge radiate E field. Right? Okay. And there's a B field, in this case the B field, so it goes outward like that, right? So you have an E cross B that's non-zero. So initially, in the initial configuration, there is already an angular momentum. And basically, the whole angular momentum is conserved. Angular momentum, mechanical angular momentum, and electromagnetic angular momentum is conserved.
So it's not because of the force on the coil, the force on the ring. Since there's a force on the ring, there's also a force on the coil. And the coil wants to spin.
There's a Newton's third law, right?
Yeah.
Yeah.
That's not, because if you're holding the ring, preventing it from spinning, then the Earth must spin a little bit. So
Yes. Right.
Sorry, if you're holding
I'm
the
not
coil.
gonna say no. I mean, I haven't analyzed this a long time, right? But that's not enough because you have to take into account the angular momentum and the momentum in the field. If you analyze it properly, and I have to tell you the truth, I haven't. So I'm not going to say no, right? But I'm saying that this is something that you should think about.
So,
yes.
I guess what's confusing is like if angular momentum is like defined as d tau dt, right?
Yes.
So like in that case, does that mean that since the angular
No. Tau is ddt.
or tau, okay,
Yes.
but does that mean that like, because in this case the angular momentum is like transferring between like mechanical angular momentum and you said like the momentum in the field,
Yes.
does that mean that you have some sort of torque that's turning that into like
Yes,
converting it into the field?
Right. So basically what happened is this is going to be very complicated because there's all this back reaction, right? Anytime you start to have a Faraday's law and Ampere's law working together, you have all this back reaction that goes back and forth, right? So, but you are right there, because what happened is that as these things start to move, that the field, the angular momentum in the field start to drop, right? So that the whole thing is conserved. And you can analyze this actually.
So by Newton's third law, when something has a force on it, it has to put a force on something else. That something else is the cross product of those two fields.
That's, yes. Correct.
So we're putting a force on E cross B.
You're putting a force on. No, you'll change the configuration of the E cross. You'll change the configuration of the electric field and magnetic field.
So what are
So
we?
the E cross B will be different.
Are we moving something else?
I shouldn't have brought this subject because I haven't thought about it very carefully enough. I'm just using this as a platform so that you understand, you go study more. To tell you the truth, I haven't analyzed it properly myself lately. But yeah, this is the kind of thing that you want to think about. Right? And the reason I brought this up is because yesterday we were talking about displacement current in the Maxwell equation, right? Remember displacement current, right? So how come Faraday didn't discover it? I mean, he's such quite the greatest experimentalist ever to live, right? Why was it discovered only theoretically? And only later proven? Proven like 50 years later, or 30 years later, 40 years later. I mean, a lot of people ask me, some people ask me this question, that's the reason I ask. But there is an answer again. Also for the future, right? I mean, you can analyze that and then calculate that. Turns out that the effect is smaller. For now, I'm going to just say, right, back to Maxwell equation. I know many of you were not there yesterday. Right? Any question on the homework? By the way, the rest should be pretty straightforward. I think these are the three more complicated ones. So this is before Maxwell, right? Coulomb's law, Ampere's law, right? Faraday's law, right? Okay. And Faraday was able to discover this, right? But suppose, let's pretend this is just my speculation there, and I think, who knows, right? But suppose actually there is a magnetic monopole. Right, so you have epsilon now. Right? And then you have del cross B is equal to mu naught J, and then del cross E is equal to mu naught, something else, right? Epsilon naught maybe, right? This is why I don't like this SI unit, magnetic current. So when you already, if you have something like this, I'm willing to bet that Faraday is not going to be able to actually find that. Because what happened is this thing that Maxwell derived theoretically. This is like the first, probably the first theoretical speculation, right? I mean, before that, even from the time of Newton, right? You have observation and then you try to find a theory for it, right? This is the first time, which is the genius of Maxwell, right? He introduced a new term that wasn't there at all before, right? Epsilon naught dV. There's a fact, you can analyze this, and I'm not sure if maybe you really want that or not. It's actually much smaller than that effect for low frequency stuff. Right? So this thing is not, it wasn't discovered experimentally until, you know, much later when you can actually observe a spark effect at high frequency. right? Because this has a time derivative. So this is actually way smaller than that, completely small, right? If you want to actually derive, if Faraday wants to actually find this by experiment, he will be swarmed by the Biot-Savart law. Right? The Biot-Savart law will be just way too big, and then he won't be able to see that. And that's what happened. So if you have something like this, right, then you by symmetry, right, you have minus dD, and here plus dD. Right? This is all of factor too small compared to the real curve. I'm not sure why. I think I'm responding to some question before something. But yeah, that's the reason.
So is the reason why there's no Jm term in the del cross B is because there's no magnetic monopole?
Yes, because there is no magnetic monopole. I mean, at least maybe you might can find it eventually, right? It's an astrophysical phenomenon, right? As of today, there is no experimental evidence for a monopole, right? Except there was one at Stanford, right? Isn't that, when I was here in undergrad, I don't know, maybe it's part of the joke between Stanford and Berkeley. They said that they found one evidence of it in Stanford in the 70s, but not reproducible at all. Is that true? Is that true? Do you know? Does anybody know? Is it just hearsay? Maybe I don't know, but in any case.
I know they've been able to make a quantum monopole, or some like some quantum particle configuration that behave like it's not a magnetic monopole, but it behaves like a magnetic monopole would behave.
Yes.
And
yes,
but they're saying that if we can create a quantum configuration that creates something that looks exactly like a magnetic monopole would, then that's maybe a good sign that it might exist somewhere.
In the
Yeah.
universe. Yeah, that's possible. Yes. And one interesting thing, I mean, of course, this in the end, you cannot just separate physics from classical physics, quantum physics. They're all connected, right? But later on, maybe in 137, right, there is a beautiful derivation by Dirac that shows that, relying on quantum mechanics, that if there exists just one monopole, right, then you can explain charge quantization, right? I mean, it's kind of weird, right? Why is charge quantized, right? Why do you have charge? Electron is, everything is a multiple of a charge of electron, right? Charge of proton, charge of whatever, muon, tauon, they're all integer multiple of a charge of electron. Why? And there is no answer as to why, except that if you believe quantum mechanics, if somehow you make just one assumption that there is a monopole, just one is enough, one in the universe, right? And then it will explain the quantization of charge. And the derivation is not that hard, actually. It's in the standard quantum mechanics book. You look it up. I don't know, maybe Zachariah or something.
So if there isn't a monopole, then you would prove.
No, well, then if there is no monopole, it doesn't mean. Experimentally, we know this. Experimentally, there is charge quantization.
Yeah.
But we just wouldn't know the
But
reason why.
the reason we don't know, right? But if somehow there's a monopole, then the reasoning becomes so elegant, so beautiful, right? That it explains that immediately. And let's see what else. Yes. Oh, part of the reason was I was talking about it yesterday about what is a P field, what is a force, right? And that's always right. So conservation of energy and momentum is a bit more involved. If you just include electrostatic, it's actually pretty simple. But if you have to include magnetism, right? So this is where maybe you're right, that maybe actually it's a relativistic effect, right? Because there is an asymmetry there, right? But if it's just electrostatic, then conservation of momentum and energy is very simple, right? But if you include magnetism, then it becomes more complicated. That's the best answer I can give. Okay, I think it's time to go.